Hi, great minds. You're welcome to Organotopic Chem Clinic, where chemistry becomes crystal clear. In this episode of Inorganic Chemistry, we'll be cracking a powerful periodic trend, which is electron affinity. What is electron affinity? Electron affinity is the energy change that occurs when a neutral atom in a gaseous state acquires electron to form a negative ion. In other words, electron affinity can be defined as the energy released when an electron is added to an isolated gaseous atom to form a negative ion. So invariably, when an electron is added to an isolated gaseous atom, it may be accompanied by a release of energy, or energy is absorbed in the process. When energy is released, it is referred to as what? Exothermic reaction. But in an instance whereby energy is absorbed, it is regarded as endothermic reaction. In general, electron affinity increases from left to right across the period in the periodic table. That is, increase in negative value, except for noble gases and some other elements in the periodic table which possess a positive value of enthalpy. While down the group from top to bottom, the electron affinity decreases. That is, the negative value of enthalpy decreases down the group. So the addition of electron to an isolated gaseous atom can be expressed in this way. We have addition of electron to an isolated gaseous atom X, addition of electron resulting into the formation of a negative gaseous ion, which is accompanied by a loss of energy. We have enthalpy of reaction is negative kilojoule per mole. Okay, so the negative value of enthalpy here indicates that it is what? An exothermic process. If the sign of enthalpy is positive, then it implies it is what? Endothermic process. I would like you to note these exam tips. Electron affinity. What is affinity? Affinity implies loving. So when an isolated gaseous atom attracts electron to itself, we can equally say such atom loves electrons. So it is electron loving. Loving means affinity. So electron affinity means electron loving. Make sense? So why do we have an increase in electron affinity from left to right across the period? Note that the atomic size of elements across the period decreases, and also electron is being added to the same shell, which implies that electrons are drawn nearer to the nucleus. That is, we have a compression of the electron cloud towards the nucleus. And also we can observe that the atomic number of elements increases across the period. So when there is an increase in atomic number across the period, the atomic size decreases. Then the force of attraction between the innermost nucleus and the outermost electron increases as we move across the period in the periodic table. That is, from left to right across the period. Since the attraction of electron towards the nucleus increases across the period, so the affinity for electron by isolated gaseous atom increases across the period. Make sense? Why do we have a decrease in electron affinity down the group from top to bottom in the periodic table? The atomic size of elements increases down the group in the periodic table. When there is an increase in atomic size down the group, the distance of the outermost electron to the nucleus increases, which results to a decrease in the attraction between the outermost electron and the innermost nucleus. So the attraction for electron decreases down the group. So the ability or affinity for electron decreases down the group. Note that down the group, more shell is being added to the pre-existing shell. That is, the shell number increases as we move from top to bottom down the group. So when the shell number increases, the atomic radius also increases, and the attraction between the nucleus and the outermost electron decreases in the process, therefore decreasing the affinity for electron. And this results in a decrease in affinity for electron. Therefore, the electron affinity decreases from top to bottom down the group. Make sense? Note these tips for your exams. When an element exhibits higher electron affinity, such elements will love to gain electron easily and in the process lose higher energy. But in an instance whereby an element exhibits lower electron affinity, then we can say such element does not gain electron easily, and invariably it will lose lower energy. Elements with higher electron affinity are likely to be non-metals, while those with lower electron affinity are likely to be metals. That is, non-metals exhibit higher electron affinity as compared with the metals with lower electron affinity. Now, don't fall into the trap because there are exemptions to this trend. Recall that it is generally believed that from left to right across the period, electron affinity increases. But we have exemptions of elements which do not follow the trend, that is the general trend. We can observe that the elements right here are found in period 2 in the periodic table. We have lithium with electron affinity -60, beryllium +66, boron -27, carbon -122, and towards neon. It is observed that lithium has higher electron affinity as compared with beryllium. Also, carbon exhibits higher electron affinity as compared with nitrogen, and fluorine exhibits higher electron affinity as compared with neon. Then down the group, it is observed that chlorine has higher electron affinity when compared with fluorine. So we are going to justify this variation in the electron affinity of elements across the period and down the group. Note these exam tips. When addition of electron does not result into pairing of electrons, it will result into energy release, that is exothermic. But when the addition of electron results into pairing in the subshell, it results into absorption of energy, that is endothermic. When addition results into exothermic, electron affinity is said to what? Increase. But when the addition of electron results into absorption of energy, that is endothermic, electron affinity is said to what? Decrease. Now let's take this quick example to explain the exemption. I'm going to consider nitrogen and carbon. Carbon is considered to have electron affinity of -122, while nitrogen exhibits a positive value of electron affinity, that is +31, which is endothermic. We can observe that in the electronic configuration of carbon, carbon has atomic number 6, and it has the electronic configuration 1s2, 2s2, 2p2. We've discussed the electronic configuration. You can check the video right here. In the p subshell of carbon, we have this. On the p orbital, we have just 2 electrons. According to Hund's rule, electrons are singly filled before pairing occur. We have singly filled electron and an empty suborbital right here. So in an instance whereby there is an addition of electron to the empty 2pz orbital right here, it implies that new electron comes into this subshell. So we have electron moving into the subshell. In an instance whereby electron add on to an empty subshell, energy will be released. So the electron affinity will be negative in such an instance. And in this case, there will be no pairing because we have electron moving into an empty subshell. So we have this. So when the electron that is added to the empty subshell does not result into pairing, then it will be exothermic, that is release of energy. But in the case of nitrogen, nitrogen has the atomic number 7. We have the electronic configuration 1s2, 2s2, 2p3. Okay, so when we add the electrons together, we have 7 electrons right here. Can we express the electrons in the p orbital of nitrogen? We have 1, 2, 3. So we have 3 electrons in the p subshell of the nitrogen. So in the case of nitrogen, when electron is added to the subshell, it results into pairing of the pre-existing electrons. So we have spin up, spin down. So when we observe the pairing of electron in the p subshell, this will result into the absorption of energy, that is endothermic, and that causes the electron affinity to decrease, that is moving towards the positive value. When the addition of electron results into pairing, it will be exothermic. So in other words, when an electron is added and pairing occurs, it results into an endothermic process. But in an instance whereby the addition of electron does not result into pairing, it results into exothermic process. So we can as well check in the case of lithium and beryllium. You can as well confirm that of fluorine and neon. I have another exam tips for you, so look closely at this. The numbers right here indicate the groups of elements. We have group 7, 6, 4, 5, 1, 3, 2, 8. So when we move from right to left according to the numbers right here, the electron affinity tends to increase. That is, elements in group 7 exhibit the highest electron affinity. Group 7 elements have higher electron affinity as compared with elements in group 6. Elements in group 4 have higher electron affinity as compared with elements in group 5. Elements in group 2 have higher electron affinity as compared with elements in group 8. The electron affinity of elements in group 8 is less than that of group 2. Group 2 less than group 3, group 3 less than group 1, group 1 less than group 5, group 5 less than group 4, group 6 less than group 7. But in an instance whereby we are considering the absorption of energy, the absorption of energy increases in this direction. That is, the group 8 element tends to absorb more energy than group 7 elements. But when you are considering the release of energy, that is exothermic process, the group 7 element releases more energy as compared with group 8 elements. Now let's take a quick example right here from our CYK check your knowledge. Arrange in increasing order of electron affinity. We have chlorine, sulfur, silicon, sodium, and magnesium. We are to arrange in increasing order of electron affinity, that is from the lowest to the highest. So feel free to pause the video while you attempt this question. So let's solve the question together. Chlorine is found in which group of the periodic table? Group 7. The sulfur is found in which group? That's right, group 6. Silicon is found in which group? That's group 4. Sodium is in group 1. And magnesium is found in group 2. Can we make reference to the chart right here? 7, 6, 4, 5, 1, 3, 2, 8. So we can observe that in this trend, we do not have elements in group 8, but we have elements in group 2. Elements in group 2 is the least in terms of electron affinity. So it is actually less than. Do we have elements in group 3? No. Do we have elements in group 1? Yes, we have sodium. Is less than. Do we have elements in group 5? No. Do we have elements in group 4? Yes. Silicon is less than. Do we have elements in group 6? That's right. We have sulfur less than. Do we have elements in group 7? That's right, chlorine. Chlorine. So, in this order, chlorine has the highest what? Electron affinity. Make sense? If you found this video helpful, hit the like button, subscribe, and share with your classmates. See you in the next video. Thanks for watching.